Yes. Got it. Bob was the other one, right?
I remember Doug. Okay, it's 7:30 and we're going to get started. It's 7:30 and we're going to get started.
Gotta get a gallery.
I got one.
Put this meeting in order.
Yeah, if they don't stop in a minute, I'll get all my equipment out. I got two things. I got a spear and I got a cowbell. Okay. Welcome to the December meeting of the Johnson Space Center Astronomical Society. My picture for the opening slide, I didn't get any other ones, so I stuck one of mine in there. That's the Angel Nebula. Here is our agenda for this evening. So tonight we're going to have a series of short presentations by JSC members. This is going to be a really good meeting, I think, tonight. Got lots of variety. I'm really looking forward to it. Before we start, I would like to invite anyone that's the first time here to raise your hand, tell us your name, how you found out about the JSC Astronomical Society, and what your interest is in astronomy. Okay, right here.
Me?
Yeah, you.
Yes. Hi, my name is Boaz Barjo. I'm a graduate student here at the School of Biotechnology. I found about this meeting on the meetup.
Meetup. Great. Nice to have you.
Thank you.
Welcome. Umberto, you want to tell us about yourself?
Hi everyone, I'm Umberto Sainz. I'm worked up on the northwest side, a startup company making HTS wire, superconducting wire. I live in Lake City, so I started off looking, Google searching and stuff like that, and popped up the parks there in Recreation. They have that first Saturday of the month one with it's
League City.
Don Roy.
Dan Roy. Yeah.
And then I just did some Google searching stuff like that and found out about this one. So it looks pretty interesting and want to learn and figure out how to buy a telescope, something that's good, and look at the pretty stars.
Excellent. Thank you. Anybody else first time here? Right there.
Hi, I'm Jennifer. So I found this place because I needed help with my telescope, so I wrote an email, and like 3 months later, is it Doug? Did I answer me?
That's me.
Thank you for answering.
I try to stay incognito, but that's me. Yes.
So, you know, when you mentioned that they had, you know, this was the club, I was like, cool, awesome. I listened to the last, meeting on YouTube, so. But I got my interest because my dad was, worked for NASA at JSC in the late 80s, early 90s, on the payload projects. So pretty much anything to do with space or science is just pretty much in my blood now. So.
Great. Well, we're glad you're here. We will get you figured out on your telescope. Anybody else? First time here? I think I know everybody else. All right, good enough. Okay, we have two email accounts. One of them is for meetings only. You can send that to his top email address, Ron, and Ron's sitting right up there. He'll put you on our meetings only list. Or if you want to get all the emails, you can send to David at the Starhopper email address here. If you can't get that copy down quickly, at the back of the room, there's a clipboard with some tear-offs that has those two email addresses on them. You can tear that off, and it has both of the email addresses on the tear-off tab up there at the back table. Okay, reminder to presenters. We got a lot of presenters, so pay attention, because most of the time I say this, the presenters aren't paying any attention to me when I'm telling this. Okay, if you're a presenter, you use this mouse pointer that's built into this laptop doodad here. That's so the people online can see what you're pointing at. Don't point at with a laser pointer. Nobody can see that. Use the one that's built in here to this little mouse pad doodad. Okay, the stream mic is built into this laptop. The auditorium mic is right here. So you can't go anywhere. You can't stand over there or stand over there because nobody can hear you. So you got to stay right here, kind of in this area. I know people like to move around, but that is just too bad. You got to stay right here. Another reminder, please no conversations in the auditorium during presentations. So don't pick up a conversation with somebody sitting next to you and start yakking, because it makes it difficult for the people in the auditorium to hear what's going on with the speaker, and it's rude to the speakers. The second thing is, please don't do anything with your phone that actually makes noise during the meeting, because that's distracting also. We've been having a lot of problems with this. I'm just asking everybody to be polite to our speakers. All righty. Our first presentation of the night is Mark Junko with my experience at ESP and globular clusters.
Right or left to slip?
What?
To go, it's right or left?
Yeah, I didn't tell. Okay, I should tell everybody that too. If you want to go forward, just hit enter. If you want to back up, hit the backspace. Right, Trevor? I believe that's correct.
Forward is enter.
Enter and
Oh,
back,
okay.
and back is backspace.
All right. Hello, everyone. I'm kind of a beginner when it comes to these star parties, and the ESP was the first star party that I went to. Kind of new, so wasn't sure what to expect. And it turns out when they have these events, they have it when the moon's not out, and that's like the only thing I could find at night. So, so right away, I was already looking for help. Let's see. So, okay. All right. So I had two options. I needed guidance. Al's set up right next to me to my left. So you don't see his rig there to the left, but that's my telescope with our club sticker. I could have asked him every night what to look at, but I think that would have gotten annoying. So what I chose to do was go to the ESP website. The ESP website has observing programs where they post a list of things for you to look at, and as a guide. And those are the stuff that's up for that night. So instead of bothering Al every night, I chose to go with this option because it comes with a prize at the end. If you fill it out, the date and the time, and you turn it into one of the administrators, they give you something. So I'm like, I like doing stuff and getting things. So that's kind of cool. So I started doing this. And as I went down the list, I noticed it was front loaded with globular clusters. And I was thinking to myself, I know what a globular cluster is. Globular, spherical, cluster is a cluster. Pretty straightforward. So I'm looking at this stuff with my telescope, backing it up with my C-Star. And these are some of the pictures I was taking that night of globular clusters. And I thought to myself, there's got to be more to this. These globular clusters are really cool. So the next day, I did a little research, and I'm going to share with you. These things are made of hundreds of thousands of stars. The diameter is about 60 light years. The average distance between the stars on these things are 1 light year. And when you get closer to the center of these clusters, it's like up to a 1/3 light year. For perspective, our solar system is 3 light years. So if we were located in a globular cluster, we'd have almost 10 stars, 10 to 6 stars within our solar system. So that's kind of crazy. These stars in the globular clusters are like the grandparents of our stars because they're older stars. They're population 2 stars, which are light in metals, meaning not a lot heavier than helium located in those in these stars. Unlike our sun, which is a population 1, which is heavier in metals. So these are kind of like the grandparents, not the great-grandparents, but the grandparents. Now, I call it the antisocial grandparents because they're not located in the plane of the Milky Way. Our Milky Way is like a disk, but if you cut that disk and you look at it sideways, if you look at the graph to the right here, the globular clusters are actually located in a sphere around our disk. So they're kind of on the outside looking down and around at us. So they're kind of unique. So I really didn't, the first day I was looking at it, I just thought they were clusters, but it's more than a cluster. These are ancient stars that aren't even in the disk with us. So I know I got 2 minutes, and I think I'm at 3 minutes. So I think I went over. So once I finished the checklist, I had to go get my prize. And so I sought out Bill Flanagan. I believe, can someone correct me if I'm wrong? Is this Bill Flanagan?
That's Bill Flanagan.
Okay. He gave me my prize, which is the button that I'm wearing right now. So there is a prize. So don't let them fool you. Thank you.
All righty, next up we have Forrest Lumpkin with variability of our star. Woo, Forrest!
All right, enter to go forward. There we go. So my name is Forrest, and I am not, little disclaimer here, I'm not much of an astronomer, but I am a recently retired rocket scientist from NASA. So 2 months ago when Doug asked me to speak about an astronomy subject, I had no idea what to talk about. And one thing I did have to learn about astronomy in my job was that our sun is a variable star. So I'm going to talk about that. So our star, also known as Sol to some people, the question is it variable or not? And I'm just going to go right to the answer, yes, it is. But it's not very variable. It's called almost stable variable star. When we think about your classical variable stars like Betelgeuse, they vary in luminosity or in magnitude. It goes from magnitude of like 0 to 1.6 from its brightest to its dimmest. Whereas our sun, it really only, even though it's a main sequence star about halfway through its 10 to 13 billion year life, it only changes in its brightness output about 0.1% over its 11-year cycle. Now that's not change in the solar radiation at the top of the Earth's atmosphere because the Earth's orbit around the sun is not circular, it's elliptic. So actually we're about to get as close to the sun in January as we are at any time during the year, which is counterintuitive to us in the northern hemisphere because that's when it's coldest in the northern hemisphere. Okay, so why is it variable? Well, it's got this solar dynamic cycle where the magnetic polarity reverses, and I'll say every half cycle. Even though we talk about an 11-year solar cycle, it's really a 22-year cycle because in 11 years, north flips with south and it stays that way for another 11 years and then it flips back. So a full cycle is 22 years. So why do we care about this? Well, as astronomers, we care about things like sunspots. Some people in our group care about space weather, especially if you're going to go on a little trip with Paul Maley and go watch the Aurora Borealis, or the I guess he even does trips maybe to see Aurora Australis. I'm not sure. And in between, when there's not a whole lot of solar activity, maybe he just does eclipse tours. I don't know. So anyway, let's see. Oops, I went the wrong way.
Keep pressing. Keep pressing. Keep going. Now you're in Mars. Keep going. You're getting there.
Push the wrong button. Okay.
That's you. There you
Okay. Oops. Now I got to go backwards. Okay. So what happens during a solar cycle? Well, everybody's heard of solar maximum and solar minimum. And the way we count solar cycles, and I don't know who came up with this, it's somewhat arbitrary, is we count from one solar minimum to the next, and that's an 11-year half cycle. We are currently just past the solar maximum. That was about the end of 2024 and early 2025, and it's solar cycle 25 that we're in right now. That's because they started arbitrarily counting them sometime about 300 years ago, 275 years ago, something like that. So solar minimum, there's few or no sunspots. And people have known this for thousands of years. I guess the Chinese noticed it a long time ago. But it's also at its lowest brightness of that 0.1% variability, but it really has the lowest ultraviolet irradiance. And that's the important part for us here on Earth. At solar maximum, we get the maximum sunspots, maximum brightness, and the highest ultraviolet irradiance, especially at the extreme ultraviolet. Make sure I get this right. Is that enter? No. Okay, so a picture's worth 1,000 words. Here's 400 years of sunspot observations. I got this off of Wikipedia, and you can see that 11-year solar cycle. But you can see some other curious things going on, that the magnitude of the peaks changes quite a bit over time. So it's not like a perfect periodicity. The other thing that's not really apparent in this is that 11-year solar cycle, it can vary from like about 10 years, a little less than 10 years to 12 or 13. And then there's periods where the solar cycle just kind of goes away altogether. There was a period that you might have heard of back in the 1600s called the Maunder minimum, where it just, the number of sunspots went to almost zero for a 50-year period. Then there was the Dalton minimum. A lot of people thought that was responsible for the little ice age here on Earth. Other people think it was due to volcanic activity. So, at any rate, that's what a solar cycle looks like. So, what has that got to do with my job as a NASA rocket scientist? Well, during solar maximum, us here who care about the International Space Station know that the drag on the ISS, all other things being equal, is the highest during solar maximum. So let's go back to the radiative output of the sun. There's a thing called the solar constant, and it's about 1368 watts per square meter. And that energy is spread out spectrally. About half of it's in the infrared, very long wavelengths. 40% of it is in the visible, which is what our eyes are designed to see. And 10% are very short wavelength, high energy ultraviolet. So we are currently, like I said, near the solar maximum. And during solar maximum, at the shorter UV wavelengths, that extreme UV, the output increases at those wavelengths, not 0.1%, but 1.5%. So what does that do to the Earth's upper atmosphere? Well, we have this thing called the ozone layer. Perhaps you've heard of it. It's up at about 78 to 80 kilometers and a little bit high. It goes up from there a little bit. And it preferentially absorbs almost all of that extreme ultraviolet. And what that does is it increases what we call the exoatmospheric temperature. If you look at the temperature versus altitude for Earth, it goes through all these various changes, and those are what separate out the troposphere from the stratosphere, from the mesosphere, from the thermosphere, and then finally we get to the exosphere. So at solar maximum, that exoatmospheric temperature goes up to about 1600 Kelvin, whereas at solar minimum, it's down at 600 Kelvin. So that's quite a wide range, and that's all because of absorbing that extreme ultraviolet light. So what happens to Earth's atmosphere at the upper atmosphere? it puffs out as a result. So therefore, during solar maximum, all of the things being equal, the ISS orbital decay can go from something as low as 1 kilometer per month up to like 3 kilometers a month. And that's not KKM, it's not megameters. It's typo, Phil caught that, at its maximum. So we have to do a lot more progress flights up to the ISS at solar maximum to get the fuel required to do the reboosts. They mitigate that a little bit by flying lower during solar minimum and higher during solar maximum. That's about it. Anyway, that's all I got.
Okay, now I know you guys are thinking you're going to wait with me without me saying anything about radio astronomy, but I'm just going to point out that during the solar cycle in the radio wavelengths, it changes dramatically throughout the solar cycle, like 1,000 to 1 in the radio wavelength. So, but I'm not going to say anything more about radio astronomy this meeting. Okay, I promise. Next, what?
Well, the radio frequency at 10.7 centimeters. Even though that's not extreme ultraviolet, it's a very close analog to the ultraviolet light that comes out. So we've been measuring that since 1946, not we, but the Canadians, to put it into our atmosphere model. So you'll see F10.7, those are measurements of 10.7 centimeters, sorry, which is a radio wavelength, not an ultraviolet wavelength.
So, Forrest, you know, like what percentage it changes at 10.7?
It goes from, it's like about a factor of 3.
Yeah, it's pretty big.
Solar min to solar max.
Yeah.
It's significant.
Big. It is big. So, okay, next up, Al with making an artificial star.
I noticed nobody was asking questions, but this last speaker, I'm sure we could ask him a lot of questions. I have a lot of questions. So, does everybody know what an artificial star is good for? We're going to talk about that. You can buy them. I didn't show any bought ones, but I think, I don't know, $50, $75. Used for testing optics, refractor testing, collimation. I put one together because I wanted to play with my focusing software through K-stars. And I didn't want to wait until a good night was going on to spend a lot of time doing that. So I figured if I had an artificial star, I could futz around with some of the software and be way ahead using the bat mask and stuff. So here's a couple designs. The one on the left uses I think a sprayer tip nozzle for a paint sprayer or something else attached onto a flashlight. And then this contraption on the right. Whoa, pretty sophisticated, but I didn't have time for all that. So I ended up with this design here. I brought it in just because it was easy. And what I like about it is it uses a flashlight, so you don't have to use like an LED and a battery and all this junk, and a simple pinhole, and then an eyepiece. The eyepiece helps because it will make the dot a little bit smaller than the pinhole is. And it also presents like a light front so that you don't really have to be dead on. This flashlight one here on the left, I mean, that's got to aim right at your scope. I mean, pretty much be aligned up. And with this one, yeah, if it's not completely lined up, maybe you won't get a perfect circle, but it's okay. And so oddly enough, I found this from Reddit. I looked and looked. I looked at many, many different designs. And this is a picture from Reddit of how he put it together. Flashlight on the right over here. And then in order to do the pinhole, he was using PVC and he did this. And then a cap over here. And then this is his eyepiece over here. But I went with a slightly different method. And this is going through kind of like what's good about it. Here's a picture of theirs using a standard tripod. And what was great about it is I already had most of the pieces. I even had an eyepiece, an old Plossel. So this is a picture of this broken down. So this is basically together. This is the flashlight. This is a pinhole that I 3D printed. And this is an eyepiece. And then over here are the components. So this is an adapter to hold the flashlight. This is the pinhole. This is an adapter to hold the eyepiece because the tube's a little bit bigger. And this is the eyepiece over here. And right over here, you can see my little pinhole. I 3D printed these and I didn't want to come back several iterations of making a pinhole. So I made one very large in case I needed to use like a piece of foil and put a hole in it. And then I made two other sizes, like 1.5 millimeters or something like that. I didn't truly know the printing resolution, so I didn't know if I was going to get a 0.5 millimeter hole, but I figured a 1 millimeter I would do okay. And so that worked out really good because I got a really nice little hole. Yeah.
So I'm not understanding, where's your pinhole in this? On this pinhole?
Okay, so here's the location of the pinhole.
Okay, the pinhole's like in the middle.
Right in the middle. You know, the guy in his discussion was talking about needing a certain length tube and this and that and the other thing. And I didn't see that it made that much difference. It's not like they said something like the eyepiece is presenting like a negative lens, but it's not like I was doing about 30 to 50 feet, which is very nice, comfortable distance. I tried different positions. That's why I used this kind of crazy tube here, because I wanted to see if there was some variability, because I didn't really want a couple foot long tube and stuff. And he was trying to say that it made a difference, but pinholes are like fixed focus, like infinity. Right. So there's no focus point there really. And then an eyepiece, well, you're not going to really focus it onto something because you're not like 2 inches away from your refractor. So I didn't get it. I didn't find any big difference. So I put the pinhole here anywhere. And what I did when I made the pinhole was I made two cones. I made a cone on this side and a cone on the other side, so that the pinhole part was only about 1 or 2 millimeters thick, because I made this about a 1/2 inch wide. This part here is about a 1/2 inch wide. I can take it apart, but I didn't want to put a hole through a 1/2 inch of material because I figured it'd get obstructed through the printing process. So I made two cones so that the actual part of the pinhole was very short. Does that make sense? Because normally a pinhole you'd use foil or something like that, and there's a whole technique to making pinholes. I didn't want to get all involved in that. So I was so happy that the printing worked. So here's a couple pictures, and hopefully this particular presentation is saved online, and you can go back to these pictures. I found this somewhere else, but you can see some astigmatism problems. You can see coma misalignment, the second set here. This is a typical problem in refractors. Always good to check at least once. Mine's home built, so I haven't quite gotten to this step. Spherical aberrations, that has more to do with mirrors. And then turn down edges, once again, more like mirrors. And then zones, that has to do with mirrors. And then the very last one down here is perfect optics. And what I really like is the center focused picture, because you still end up with a little bit of a halo. This has to do with diffraction. You're gonna, even at a focus point, you're still gonna end up with a little bit of diffraction. And I think that's the last slide. Let's see. So there's probably other good uses for this. It's not just used for refractors, but I know testing focus, that's what I used. And then lens defects, as the pictures before showed, but maybe some other people know of other possible uses, or maybe we'll find some new possible uses. But you know, the eyepiece is an old Plossol. I mean, you can get Plossols online from China for like $10, and a scrap piece of tube, and the flashlight I already own because it's just an LED flashlight, you know, cheapo flashlight. So pretty much I put it together pretty inexpensively. And once you have one, you can share it with your friends. I think that's the last slide. Yep.
So just one more question. So did you guys feel free to ask our speakers questions, right? So do you feel like there wasn't any difference between the distance between the eyepiece and the pinhole? Didn't make any difference?
No, I think ultimately they're supposed to be between the pinhole and the eyepiece. I don't think there's any difference between the pinhole and the flashlight.
That's what I mean. Between the pinhole and the eyepiece, you have to move the eyepiece around? Or?
I tried it, you know, this is a shorter one than he said that you should use. Yeah. And what I was really looking for was, if you have an arbitrarily large pinhole, you have to have it pretty far away. Right. but I have that 5-inch refractor with a 700 millimeter focal length, and I was able to do it just from the garage, like out into the driveway, like 30, 40 feet. It wasn't like huge distance, so that was really nice.
Ambient light impact this at all? Like reflecting off the tube or the?
Good point. I did have a little bit of an issue with the background. So at one point I tried doing it like put a black background behind it, but depends on what you're doing. If you're using like live video where it's a really fast repetition, all the background's going to disappear, right? It's only going to be that. If you're going to do a longer exposure for some reason, then yeah, probably the background's going to make some difference. But yes, not daytime. This is still nighttime, or or in dark room or something like that. This wasn't daytime at all. This is nighttime. Good question though.
Okay, so Paul is going to tell us about celestron origin imaging with an equatorial wedge and a 768C camera. Paul,
So I presented here, I've had the origin since July 2024, and I presented some early results with it. So this is kind of an update on some new features and equipment that have come with it, that have been released. All right, so first of all, Origin now in its firmware, software supports an equatorial wedge, kind of following along with what C-Star is doing, I guess. You can purchase a wedge from Celestron, same one that goes with, it's basically, it's, a modified Nexstar, what's the word? Evolution mount, there we go. So anyway, the advantages of polar alignment, just to review, probably the most important one for me is no image rotation. So you can image for a longer time and in longer overall exposures. And you can image at the zenith, which is reason number 2. That's usually the best part of the sky, not always. And then perhaps less important to me, you can do longer individual exposures, but Celestron says you can go up to like 30 seconds, but then the default is 10 seconds. So not sure how much it really matters. I've just been using 10 seconds so far. So disadvantages, obviously the wedge is an extra piece to carry, and it weighs a little bit. And then it's a few extra minutes each time to initialize. So this is what it looks like. To set this up, you really just point it, first of all, set up the mount so that it's pointing to the north, and I just use a compass on my phone to make sure that it's roughly there. And then Celestron the app tells you where to go, basically, to align it from there. And then it just takes a few minutes to do that. The app tells you what your error is. You do have to use an Allen wrench to move the azimuth mount. And once you've done there, you've more or less hit the bullseye. Then it does a partial reinitialization after that. So anyway, it just takes a few minutes. But you don't have to see Polaris. From where I usually observe in my backyard, there's a tree. You can't see Polaris, but you don't need to. It just points up, basically, figures out where you are. And just as a side note, the Origin also now supports the auto guider, StarSense auto guider. There we go. I don't have that. I'm not sure. Honestly, it really helps a lot, considering that it's, especially with the shorter exposures, 10-second exposures, it's pretty much tracking anyway. Okay, and the more important thing here is that the Origin does one of the main features of it is you can upgrade to a new camera. So Celestron released the Origin Mark II just in October, and with that they released it. The main feature that it has is the 678C camera. The main things for it, pixel size is a little bit smaller, so a little bit better resolution, and instead of 6 or so megapixels, it's 8 megapixels, and the field of view, the aspect ratio of the field of view has changed, which I didn't think would be such a big deal, but it does actually make it pretty easy to do the presentation because it just fits the size, fits the screen size fine. Okay, and anyway, the important part, one of the main reasons you get the camera, get the Origin, is you can upgrade to the new camera. So it's physically it's very simple. Just unscrew the other one, and there's really not much to it. Took a few minutes, and then the new app. Once you had that, even before you have that, it would always prompt. It would prompt to take new darks and flats. Maybe that was an error actually, but then anyway. But so I ordered the new camera, and for flats, if for darks, it's easy. Just put it in your closet. That's what I do. Put the cover on and make flats for darks. But for the flats, there is a third-party tool that Celestron recommends to do that, but it was back ordered because everybody's trying to do this at the same time, not surprisingly. So I took sky flats following the procedure that Celestron recommended. It was pretty easy, but I wasn't too thrilled with the results. I'll show them and you can see what you think. And then since it was back ordered, some people recommended getting a tracing pad, so I ordered one. Costs about $14 to get an A4 tracing pad and just put it on top, and it was nice and easy, and it worked pretty well. And I have now the Giotto flat field generator, and I have taken the flats, and I went out on Wednesday night to look at it, but I don't have any pictures from that in here. So we'll see how that goes.
Okay. Oh, I got a question.
Yeah.
What was the difference between using these two? Was it the same or?
The A4 tracing pad or the Giotto?
Yeah.
I don't know
One's
yet.
like 10
I've only
bucks,
did,
the other one's way more,
it
right?
costs a lot more. There's no doubt about it. So far, I don't know. I would say I've only taken a few images with the Giotto, and I can't tell a whole lot of difference right now. So,
Right, that's what I'm wondering.
Yeah.
Okay.
But we'll see, as I go along a little bit.
What's the Giotto cost?
Like $300, something like that. It's versus 14. So yeah, there's a big difference.
Well, there's probably some kind of integration that can go into the computer.
Well, it does have a USB port to it, or you can just plug it in. But the Giotto does have, you can change the brightness of it, but they tell you to pick one setting anyway.
Do that with the tracing.
Yeah, you have to really just plug it in. So unless there's really a remarkable difference in the outcome, you might just stick with the tracing pad.
Trevor, what is your point? I was saying that could be probably integrated into whatever software he's using with his system. Whereas the
Yeah.
tracing pad's probably just a light at that point.
If you plug in the USB, I guess, into the computer, I think you can control the brightness of the Giotto from the app. But otherwise, you control it from the Giotto app, which is what I did. So there's not really a whole lot of benefit.
Question here. For your tracing pad.
Yes.
How difficult was it to try to get the right exposure time?
Oh, so you don't really, you just turn it on. All you have to do is put it on top, plug it in, turn it on. Okay. And then it just has to be about the right brightness, but it's just a series of exposures that it does, that the firmware does. So there's really nothing to it.
It's really easy. I got one that's really easy.
Oh, I know I'm doing it. I had a lot of trouble. And of course, I got a tracing pad too from Amazon or whatever, for $20. And I was trying to, I went to the lowest light level, and I started going in with, 2 seconds and 3 seconds and everything. And it would go from white to almost dark, and I'd have like one little one that worked. And then I was reading through the camera manual, and it said, if you put it on auto, when you're doing flats, it automatically finds the exposure time.
Okay.
It
Yeah.
came out perfect.
Yeah. So I don't mess with the light here or anything. It just does it does all that on its
Yeah.
own. Yeah. So yeah. So there really isn't much to it.
What I thought would be easy just wasn't.
All right. So after Skyflats, this was with Skyflats, and I don't know if you can really see too well on there, but there's gunk going down there. So it's not perfectly clean. Let's put it that way. And then with the tracing pad, these are without a wedge when I went to George Observatory. So I'm only exposing for about 10 minutes or so. So I just thought there's no reason to carry a wedge up there. So here's M16. I think that's pretty good. And then the Dumble Nebula. And then with a wedge, I think there's still a little bit of noise. But anyway, here's the Fireworks Galaxy. And then the Sculptor Galaxy here. And then I said some of the best. So the Pleiades, I think I did pretty well with the. So this one, I mean, this is the other thing is you can easily expose for, well, for me, a pretty long time anyway. Just because you also are using, I mean, also using the equatorial wedge. And then the Bubble Nebula, and this was, so it does, it's the default exposure time, ISO is now 1,000 for the camera instead of 100. And that you do tend to see things a little bit brighter. And in this case, when I had been imaging before, I never saw the entire bubble around. So this is kind of fun to see the whole thing, just with a longer exposure, etc. So that's really all I had, but that's what we got.
Okay, so
Yeah.
Paul, one question for you. Does this system dither between the images?
No, I don't think so. Anyway,
Okay.
not to my knowledge.
What's the size of the tube again?
6-inch aperture.
So just having two cameras, flush one, 178 and 678.
Correct.
But do they have plans to have other ones, do they say?
Yeah, I mean that's the idea is they'll keep releasing new versions, etc. So as hopefully they'll continue to be getting better and and upgraded. So the idea is as a whole the system is upgradable. That's the main concept, both in firmware but also in the hardware. So.
I've only used Skyflax. I've heard about the tracing pad, but does it really do a lot better job
Then what?
than Skyflax?
Yes.
Yeah, I found very much so. Now, in all fairness, I did also do new darks at the same time, but I'm pretty sure that wasn't it because it's pretty much the same thing. But the Skyflats, there was a lot of noise.
Yeah. Brandon, where Brandon went, he was the first one to discover the tracing pad. There he is. Yeah, you can count him for the discoverer in our club and that thing. It's really easy to use and does give you better results than Skyflax.
Yeah, do it inside and all that good stuff. So that's it.
All right, thank you.
Okay, we got Brandon with our location in the universe. I heard someone say something about the lights. This is as good as it gets. If you can figure out how to turn that light off, bring your gun next time. But that one stays on. This is the maximum that we can get turned off. So sorry. So enter goes forward and backspace. We can go back. I don't think we clap for Brandon.
All right. Hey, thanks everybody. I'll warn you, I'm not a do-it-yourselfer. So this is a little bit change pace here. I've done a lot of talks here in the past, and if you guys remember, I'm more interested in things like like origins of the universe. How big our universe is, which is what we're going to talk a little bit about tonight, and then other features and so forth. So Mark, your talk wherever you're at, yeah, you actually kind of mentioned a couple things about the size of our universe. That's a good lead in. Before we actually talk about our universe, right, we're talking about let's say our solar system, right? If anyone paid attention to Mark's talk, how many light years did he say our solar system was? Do you guys remember? You can't answer. Yeah, 3. Yeah, some places say 2. It really depends because it's like where is the boundary of the universe or of the solar system? So I don't know if you guys can see that, but so the pictures get a little bit better. This is our solar system. The dot in the middle is our sun, and I don't know if you can see a ring around there, but anyways, we're just going to start here. And so I don't know if you can see this kind of dusty cloud. I have the cursor kind of going all around it. Right, that's the Kuiper belt. Right, that basically starts around like Neptune, basically. Right, and it has a certain thickness. How many light years is it Well, first of all, what is a light year, right? Do you guys know what that is? Like how far is a light year? Any ideas? Yeah.
6 trillion miles.
6 trillion miles. Yeah. Yeah. It's, so to get an idea of how, that we can't visualize what that is, but if you could go to the sun and back 32,000 times, that's how long the light year is. All right. And so it's pretty far. It's the distance light travels in a year. Okay. So when we look at our solar system, like this is not showing the full boundary out to 3 light years, but if you go out to Neptune's orbit, it's basically 0.001 light years. So our solar system extends way past that to the Oort cloud, and it's kind of nebulous. I've seen 2 to 3 light years for the range on that. Now, when we look at our galaxy, any ideas, any guesses on how many light years across is our galaxy?
80,000.
Yeah. Generally, we hear 100,000 is kind of thrown out there. Again, it's not a precise measurement. We're about 26,000 light years from the center. And on this picture, you probably can't see it, but this is the Orion spur, and our solar system is right there, right? And so we're 26,000 light years from the center of our galaxy. Okay, so each slide is we're kind of stepping further and further out. And so our galaxy, the Milky Way, is part of the local group of galaxies. Our nearest neighbor of a large galaxy that's not a satellite is the Andromeda galaxy. Any guesses on how far that is from us?
2 million. Like
All right, you can't answer anymore. 2.5, yeah, 2.5 million light years. Yeah, 2.5 million light years. It's on a collision course with us, by the way. But so in this picture, the Milky Way is down here in the lower right, and Andromeda's here, and that's Triangulum. That's the next biggest one, and we can easily see those in the night sky. If you're out in West Texas, you can see Andromeda with your eyes. Now, the scale size of the local group, 10,000 light years or so. That's typically what's published. Okay, so our local group's part of a cluster of galaxies, a bigger cluster. There's a Virgo cluster, and then there's the Virgo supercluster, right? So this is showing kind of the Virgo supercluster. So where you see all this red text here is where our local group is. And when you start getting further and further out, you start to see galaxies starting to cluster together. And so the scale size on this particular image, let's say, or artistic rendition, they've actually done measurements, but the Virgo supercluster is about 110 million light years across. And so, we're just getting further and further out. And then stepping out even further, the Virgo cluster is really part of a couple of other clusters connected called the Laniakea cluster. And again, the local group is this blue text here. The Virgo cluster is in here. It's the name of it's here, but we're kind of on the periphery. Sometimes it kind of flips these over, but as you can see, we actually can get ground-based telescope, pictures of all of this, and they can put these maps together. And so these are just computer-generated images. But the Laniakea cluster that we're in is 500 million light years. Okay, and then stepping out a little bit further, I don't think they have a name for it, but it's our local group of superclusters. And so on this scale, right, it really depends where you draw the line, but I kind of looked at this one up. This is the Pisces Cetus supercluster, right? We're way over here in the Virgo cluster, supercluster. All this glow around the blue is the Laniakea. I have a different picture here in a second, but the distance to the Pisces Cetus supercluster is about 650 million light years. So, if you double that, right, we're talking, over 1 billion light years across, right? So, yeah, Al.
So, I know Pisces pretty well. I look at galaxies in the Pisces constellation.
Yeah.
So are we actually seeing galaxies from that?
No. So, yeah, it's kind of funny because there's a lot of names here that are, the constellations that we see are in our own galaxy, right? So these are just have similar names, right? Because you can see, like here, the Capricornus supercluster. I guess they like reusing names, but these are clusters of galaxies that there's no way we can see. Even with your telescope, we can't see these. Yeah.
How long ago was this structure identified?
I think they've been slowly building it. I don't know the actual date, but it's kind of a function of as we get bigger telescopes out there, right? We can see further out. And I'm going to show a video here in a second, and you'll see actual pictures that kind of look like pie charts, and they start, like wedges in the sky, and you do these scanning surveys. Some of it's also based on satellite imaging and things like that as well. Kind of backing up just a little bit, this is a little bit out of focus, but I tried to zoom in just to kind of show you, because the Laniakea is kind of a weird name. It sounds Hawaiian or something like that. But it's kind of highlighted here in yellow. And I'm not going to try to go backwards, but just remember, we're part of the local group of galaxies, right? Our nearest neighbors, we're really part of the Virgo cluster, which is a subset of the Laniakea cluster. And then that same yellow, this is just a different image. You can find these things on Google and other places, but here's like a slightly different view. So our location, obviously this is from our viewpoint, so we're at the center. But the question is, what happens when you get back up even further? And so when you go to sort of the next scale size, you start to see it kind of looks like a spider web. They call this the cosmic web. Where you get all this light here are galaxies clustering together, and on the larger scales of the universe, it looks like a spider web, and they call it the cosmic web. And these things are called filaments. And so,
So Brandon, I got a question.
Yes.
I see you got an NGC number down there. Does that mean we can actually see that?
No, I think it got shifted when I saw that after when I sent those slides in. I think that got shifted or left over. Yeah, ignore that NGC. I'm not sure that's right, because we're way up here. Virgo on this scale, NGC 315 is we'd have to look that up. It could be a galaxy. It's possible, but I'm not sure. Some of these I noticed that they're kind of inverted, and it was really hard tracking some of these. But on this scale, you'll see that Virgo and Laniakea is kind of all connected through here with these other local superclusters, but I think we're right in this location. And then finally, let's see if this works, Trevor, but if you were really large and you could go to the biggest scale in the universe as we know and fly through, this is, I think it's maybe 2 minutes. There's no sounds on this. Let's see if it works, but this is give you,
You gotta go and click in the middle of it.
How do I go back a page?
Backspace.
Okay.
Now take your cursor.
I can't, the cursor's not on here though.
That red thing.
Yeah, it goes behind the video. Yeah. Sorry, spoiler alert.
What happens if you kind of move over there and click on it?
Yeah, the cursor looks like it goes underneath the screen.
Right, but when you click on the mouse pad, it's not doing anything.
Yeah, every time I click, you want to try to look here real quick? It's actually worth looking at. While we're looking at this, so obviously, if I had to ask you, how big is the universe? What would you say? Like how big?
I'm not sure.
Yeah.
13.3 billion.
What's that? Say that?
Really, really big.
That's a good answer. Yeah. What do you think?
I think maybe infinity.
Well, that's the far side. Okay, so let's watch this video, and this will give you an idea of what it looks like. If you can imagine flying. And there's some extra information, but this is based on a computer simulation. So remember, you would have to be really big to see these clusters of galaxies, but this was what it would look like if you could fly through our universe. And while this is playing, I'll talk a little bit. So
That's Virgo.
I think that's part of the Virgo cluster and central part of Laniakea. There's several videos. If you're really interested in this, you can actually look some of these up at various academic institutions. They put these supercomputers, and this is based on real mathematical simulations, right? A Big Bang cosmology, looking at physics and how our universe changes in time and produces, right, clusters of galaxies. And so there's another one here. Now this is showing kind of like it's sped up in time, but if you watch the gaps start getting bigger, like the black spots, these are voids, right? You know, the universe had a lot of gas and energy and clumped up, you know, or not so much clumped up, but as it cooled down, you start getting the formation, you know, gravity pulls things together and you get voids developing. And so this is done through very intense supercomputer simulations. Yes, you got a question?
So those, they kind of look like neurons.
Yeah.
So maybe we're in a giant brain.
It's possible, right? So he was actually, if you wanted to estimate the age of the or the width, the size of our universe, right? We don't know how big it is. It could be infinite in extent, but on the lower bounds, right? We know we're limited by the speed of light. So right here's the actual data, by the way, of actual pictures from, or it says simulations, but actual data is on the top left. We're limited by the speed of light. We know the universe is about 13.8 billion years. So let's just say 13 for a minute, right? So you look that way, 13 billion years or billion years, and then look the opposite direction. So you could say, oh, 26 billion years. But then if you account for expansion, the lower estimate is about 46 or so billion years in one direction. So you look it up, most people say the lower limit is about 93 billion light years. So that's the lower limit. It could be a lot higher, and so we don't know how much more than that. But yeah, that's all I had there. I don't know how to stop this, Trevor. Oh, there. So yeah, that's all I had. Thank you.
Where would we be without Trevor? We would be in big trouble here. Okay, Sky and Telescope magazines. Rick, did you bring some with you?
There's 5 up there, and they're really excellent selection this month.
Whoa. Free to anyone who wants them,
I'm
right?
trying to put some excitement into this.
Okay, free. Take
They're
them.
10 years old, but they're exciting.
Yes, good. So they're free to anyone who wants those. All righty. I see Ron's here with the DVD library, but I'm assuming you guys are switching, or is that what's? Okay. Okay. We won't talk about the DVD library then, I guess. Unless you want to say something. Did you want to say anything, Ron?
No.
Okay. I got it. I took your slide out because we haven't been here for so long. I took your slide. But there's Ron. You haven't seen Ron for a little bit. He's been doing our DVD library for years. So there he is. Thank you, Ron, for everything you've done. Okay, the meeting after the meeting. When we get done here, we're going to meet at Mod Pizza for the meeting after the meeting. You just shoot up Middlebrook, take a left on Clear Lake City Boulevard, and you go past El Dorado, and right in front of the HEB, there's a Mod Pizza. And we'll get together and talk about astronomy and other things. So I hope you guys can join us. Everyone's welcome to attend. Okay, we are going to take a 10-minute break, and then we'll pick up with the second half of our meeting. 10 minutes.
You said
1 out of every 10
Thank you.
Oh, what? Okay, 10 minutes is up and we're going to get started. Oh my goodness, I have no chance of getting this started again, do I? Okay, second half of our meeting, we're going to get started. 1, 2, 3, 4, 5. Those 5 guys in the back, I'll never get them to pay attention. Guys, we're going to try to start our meeting. Yeah, you'll talk with Doug. Guys, listen, am I invisible or what's going on here? You know, I'm going for the cowbell. I'm going for the cowbell. All right, Doug's here. Yeah. Okay, you guys ready to start? Thank you. Okay, so I have a DIY astronomy, some fall astro imaging to show you. So what I'm going to show you is I'm going to show you a bunch of images from 4 different imaging configurations, going from wide fields of view all the way up to narrower fields of view. My first imaging configuration is a 16 millimeter Rokinon lens with a modified Canon 450D camera. All the exposures for these are going to be 4 minutes at ISO 200. Nobody's going to jump out of their skin about the ISO 200? Okay,
Pretty low.
I know. Okay, does that bother you?
No, it doesn't bother me.
Okay, I did a bunch of testing. That was,
It's kind of low.
it is, yeah. I usually shoot really higher
It's
ISO.
over lens, so it's going to gather a long light quickly.
It is. I did a bunch of testing. I got better noise characteristics with that ISO. And it's camera dependent. You know, I have another camera I shoot at ISO 3200. So this one, ISO 200, it's noisy. But okay, so all these are ISO 200, 4 minute exposure. I was just waiting for Stan to just jump out of the skin and say, wait a minute. Okay, so what I'm going to do is I'm going to show you a project where I went along the Milky Way galaxy, all the way from the summer Milky Way over by the Sagittarius, all the way across the Milky Way over to the winter Milky Way over by Orion. I did this at the El Dorado Star Party. I'm going to show you a bunch of wide field pictures with the configuration I just showed you. Okay, so this is the first image. That's near Sagittarius. Over here off the picture is actually the center of our galaxy over here. And each one of these pictures I'm going to show you, first the picture is going to be without annotation, and the second one is going to be the same picture with annotation. So there it is with annotation. So down here we got the Lagoon Nebula, right down there, M8. Up here, Aquila the Eagle constellation. This gigantic thing in the middle here is called the Great Rift, which you see in the Milky Way galaxy when you go out and look at it. Okay. Second one, this picture is a little farther up. Now I'm pointing towards what's called the Summer Triangle, with Vega down here being 3 stars, Vega, Altair, and Deneb here. It's a Summer Triangle, right? And here it is with annotation. You can see Cygnus, constellation Aquila over here. You can clearly see the North American Nebula up in here. You can see the Satyr Nebula, IC 1318, around Satyr there. Here's Lyra down here with Vega. Okay, going a little bit farther along our Milky Way galaxy, next stop. Here, what's cool about this picture is here's the plane of our Milky Way. And a little bit ago, Brandon was talking about M31 and M33, the Andromeda galaxy and the Triangulum galaxy. Here's our galaxy here, but looking up from our galaxy, here's M31, the Andromeda galaxy, and over here is M33, the Triangulum galaxy. So in this shot, we got our galaxy and these 2 other galaxies. Down here at the, yes.
So earlier it was said if you go over to like West Texas, you should be able to see Andromeda with your naked eye.
Absolutely. And it's really great in binoculars too. It's great. It's naked eye visible. You can also see it in binoculars. It's a really great view.
8x50 binoculars could.
The tiniest binoculars you got, you can still see it. Yeah. Yeah, this is actually near El Dorado, Texas, is where this is. One of there's multiple star parties here in Texas. There's one at El Dorado, the Texas Star Party at the Prude Ranch near Fort Davis, and another one we go to is Okie-Tex, which is kind of the panhandle of Oklahoma. But this particular set of pictures are from El Dorado Star Party. Does I see another hand? Stan.
At the bottom, you've got the Pleiades on the right and the California Nebula on the left.
I do.
And you can make out Perseus molecular cloud a little bit.
Come on up here and do my presentation for me. No, yeah.
I didn't know if you were going.
No, I was getting to that. Yeah, no, you're right. Stan's helping me out. Yeah, this is the California Nebula down here. There's M45, Pleiades. And then here, let's do a little testing. Who knows what these 2 are? Come on, Stan. What are those?
Heart and Soul.
Heart and Soul. That's right. He got it. That's the Heart and Soul Nebula. Here's a harder one. If anyone's got this one, tell me. Anyone know what that one is? That's Cedarblad 214. It's actually a really bright nebula. And I don't know. People don't seem to image it that much. That's Cedarblad 214 right in there. And this is the Alpha Perseus Star Association. And with annotation, there you can see the Alpha Perseus Star Association, Triangulum over here, Aries, and of course, Andromeda Galaxy and the Triangulum Galaxy. But what I like the most about this is, seeing these galaxies. Here's ours, and just looking up from them, there's 2 other galaxies in our local group in the same picture, which I think is really cool. So point is, I've had a lot of fun doing these wide angle shots so you can see all these things. And also it helps you a lot because you can figure out where the bright things are. You can go later and you can say, oh, I want to image that or this because it's bright enough for me to get it. If I can get it with a camera lens, I can get it with my telescope, right?
Yeah, I just had a quick question. Doug.
Yes, Forrest. Thank you. Ed.
I'm a little confused. Did you change the orientation from this picture with the previous picture? Because now the plane of the galaxy looks like it's going this way instead of that way.
Oh, that is such a good question. That is a really good question. I'm going to answer it. Okay. The plane of our galaxy is like this. Okay. And the plane of our solar system is like this. And the tilt of the Earth is like this. Okay. So this thing is always oriented north and south. Left and right is north and south. Left is south. Right is north. But when you go along the plane of our galaxy, they are just completely out of whack. The galaxy and our solar system are not lined up together at all, period. Yeah, but that is truly south, then that is north, or north and south. One way is north, one way is south. But anyway, but yeah, as you go along it, our galaxies, it's not like our solar system and galaxy are lined up with each other. They are not. Does that answer your?
135-degree tilt.
Yeah, they're way off. And then there's the tilt of the Earth also, yes. Hold on, Forrest, does that answer your question?
Yeah, I guess so. So basically the orientation is lined up with our ecliptic that we're in here. And then
Yes.
as you're moving around the galaxy, it rotates relative.
Well, okay. The celestial sphere is based on our latitude and longitude of the Earth. When we go when we go declination, it's actually zero declination is our equator.
Okay.
And then 90 degrees is the North Pole. See, so we base everything based on the orientation of the Earth. We look, right ascension is hours, minutes, and seconds. Declination is degrees based on the Earth. But when we start looking at the galaxy, it's just like, they're not lined up at all. Am I answering your question?
I think so. I've always noticed the galaxy makes, a big diagonal line across the sky.
It goes overhead. It goes overhead twice a day. Twice a day, we see the summer Milky Way go over and the winter Milky Way go over every day, but it is not lined up with our solar system.
Okay.
Yeah. Okay. Yes.
So isn't our North Star also called Polaris? So where's our North Star on that?
It is. Hold on. It's way up here.
Okay.
It's like up in here.
North, then.
Yeah. Yeah. But it has nothing to do with the orientation of our galaxy. The North Star has to do with the North Pole of the Earth. And the Earth is also not lined up with our solar system. Someone said the ecliptic and the Earth equator are not the same thing. Yeah, that's 23.7 degrees, right?
23.5 degrees.
Yeah, something like that.
And the Earth, our solar system oscillates up and down.
Right.
3.25 times.
Yeah. Stuff in space.
The upside down as it circles around the Milky Way.
Exactly. Stuff in space is not lined up at all. Okay. It's just all over the place.
So does Polaris wobble?
Well, okay. Polaris is not even actually north. It's like 0.75 degrees off of true north. And that's just where it is now. In the future, Vega is going to be our North Star. So in the future, it will change due to precession. Yes. I used to teach astronomy. Now I'm forgetting everything. Okay, yeah. Our North Star will change over time. Yeah. But just the main thing to remember is things in space are not lined up. What we use for astronomy, right ascension and declination, is based solely on our latitude and longitude of the Earth. Okay. Okay, yes, John.
So have you seen these animations where they show all of the planets and chasing the sun in a vortex fashion?
I was thinking
No.
So it makes it look like a corkscrew because we're not flat, right? Like our solar system isn't flat. It's moving like this.
Right. Yeah, that's true. Right. I haven't seen that, but I know what you're talking about. Yeah.
I was going to ask you for comments on that.
I don't have any comments. I hate to tell you, I'm an electrical engineer masquerading as an astronomer. I'm mostly interested in making stuff work. Hold on. Mayo. Oh, you're pointing him. All right, fine. Good enough. Okay, moving on. Any more questions about this one? I mean, I got to admit, this is a cool picture. What?
Make a statement there. One thing you didn't have agitated is the double cluster between the.
Yeah.
Perseus and Cassiopeia.
There's an infinite number of celestial objects in this picture.
Oh, yeah.
Yes.
That's pretty obvious.
Yeah, that's right. Thank you,
Not
Stan.
critiquing, I'm just bringing it up.
No, I appreciate that, Stan. Thank you. If you see any more, be sure to point them out. Okay. No, really, I appreciate his input. Stan's an experienced astronomer. I appreciate him helping me. Okay, this is the last one. This is down towards Orion. You're going to see Orion down here at the bottom. You're going to see Taurus. Now see the Pleiades and the California Nebula now at the top. The Alpha Perseus star association's up there. It turns out that Uranus was actually in this picture too, which I didn't know that. The thing I like about this picture, one of the things I like, this is the Taurus molecular cloud here, which I think is pretty cool. I got that in this image. And lots of things you can see that look familiar. So this is my set of pictures all the way from the summer Milky, Jerry, are you asking a question? Okay, summer Milky Way over to the winter Milky Way with a wide angle lens. Trevor.
Any chance you stitched them together into one contiguous?
Oh no, Trevor.
So this is a 6
Yes.
month.
Huh?
So this is a 6-month exposure?
No, this is a one evening exposure. This is me taking my camera, going boom, 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 taking pictures of the Milky Way over one night.
So how long did it take to produce? What time period in the year is it? Because you can't get all of them, all the clusters into.
Absolutely, you can do it all in one night. The summer Milky Way and the winter Milky Way passes over us every single day. People don't seem to get that. Just because they call it summer and winter, that doesn't mean anything. It just means where in the sky they are. But it was like, when was El Dorado? It's like in October or something. Yeah, October.
October, November, December. So Orion is available all the way back to before October. You can still get Orion.
Yeah, I mean I did this in whenever it was in October, sometime in October. Yeah, something like that. Yeah, you can see them all in one night. Yeah, but no, it's you can see this whole thing in one night. These are wide angle pictures, and the field of view, you might have missed it. It was like 58 degrees or something like that. So you think about it, I can get 4 shots. I can get the entire sky because 90 degrees would be 2 shots, 90 degrees would be 2 shots. So yeah, I can get the whole sky in 4 shots. But what's fun? This is a new lens actually. I got a Rokinon lens. I really love it. It's kind of fun. But Ron.
So did you put them all together?
No, that's Trevor just said that. Yeah. Look, guys, we can only do so much here, all right? Okay, any other reasonable questions?
What would you expect the image to look like without a unmodified camera?
Oh, you'd lose the reds. Yeah. This camera, what the modification does on this camera, it opens up the hydrogen alpha and makes it redder. Yeah.
So your California Nebula may not even show up.
I've done it with the other camera, but it looks kind of weirdish pink, pinkish bluish. I haven't done this, but I have shot it. I shot the California Nebula with another camera. It's just pinkish. It's not really red. Kind of too much blue. Any other questions on this before I move on? Andrew.
As well as, are you also stacking as well with these, or are you?
Oh, absolutely.
And then like how many stacks did you do roughly?
Oh, Andrew.
What does it say?
You're supposed to stay in front of your laptop.
I
Okay.
30.
Okay. That one's 30 4-minute exposures.
34 minutes.
30 4-minute exposures. All the exposures of all these pictures I've shown you are all 4-minute at ISO 200. You're another person that should be upset if I'm using ISO 200. Okay, ISO 200 4-minute exposures, 30 of them for this image. And the other ones, I don't know, as many as I could get, right, for each one.
This took all night.
First section?
Yeah, 30. Andrew, listen to me. And this picture right here, each one is 4 minutes long. I took 30 of them, stacked them all together. Rick's going to tell us all about stacking later. Do you understand what I'm saying?
Stacked and stitching.
What?
Stacked and stitched as well, right?
There's no stitch. There's no. One lens. This is one shot. Listen, whoever said anything about stitching, just stop saying you. Don't say that. There's no stitching. There's no stitching in this thing, guys. This is one field of view with a 16 millimeter lens, okay? Andrew, you're the only professional photographer in this room. Okay, look, this 16 millimeter lens, wide, 58 degrees, right? Yeah, right.
So that's 120 minutes of exposure when you add it all up, right?
Yes.
So to do these 4 images took all night.
Yeah.
Okay.
Yeah. Did I answer your question? Okay, all right.
You're using calibration frames as well?
Oh, absolutely. Let me tell you, if you got a 16 millimeter lens, you've got to calibrate. It will look terrible without calibration. You'll have terrible vignetting. It'll be a mess. So they got to be calibrated. And I actually did there too. Any more questions before I move on? I got more in my presentation. I'm only supposed to be up here for 5 minutes. Okay, the next imaging configurations, 200 millimeter Canon camera lens with a CCD camera. Bing. All right. Now, this image was taken when I was practicing with my equipment before the star party. And if any of you guys have ever gone to a star party with me, you know why I'm saying that. So I picked something easy at home to take a picture of, make sure all my equipment's working right before I go to the star party. Unlike some people who go to the star party, don't practice with their equipment. They get there, nothing works, and they all cry, and we all cry because it's miserable being around them. So what happens is this is an easy picture. This is the North American Nebula with the Pelican Nebula, narrow band image, 5-minute exposures, whole bunch of images. Shot these in my backyard, which is about a mile north of here. This is not at a star party. This is right here near where we are. Narrowband imaging, good pictures. This is probably my best picture of the fall, by the way. Okay, Comet C22 2025A6 Lemon. This was done at the Eldorado Star Party as an LRGB image with the same imaging configuration. You can see the ion tail and the dust tail on that, 2 tails for this comet, right? Pretty cool. Oh, David.
It kind of looks like if there's like an alien spaceship and then there's like a green light coming down.
It could be. Yes, absolutely. You're right. Interestingly enough, there's not a lot of green things in space, but comets are something that actually are green. The carbon, when the carbon burns, it actually does produce a green hue, and it's one of the few green things in the universe. Dominic.
It also kind of looks like, you see that big shining light that's going further down than the other shining lights.
You mean this over here?
No, up to the other side.
This? That's the ion trail.
It kind of looks like it kind of looks like in that dot. It kind of looks like it's like a big portal going, like cutting through the universe, and then that's like coming from another universe, and then a portal dripping through our universe.
Okay, we're going to confer with Brandon on that one because he's our universe guy, but that's a good observation. Thank you. Good. Okay, great. Thank you for that, Dominic. All right, next one. This is an area called the Perseus Molecular Cloud. I shot this a bunch of years ago with the same lens and a DSLR, and I wanted to go back and do it with a CCD camera. This one's got lots of targets in it, so we're going to look at an annotated version of it. It's flanked by 2 reflection nebula, IC 348 over here, NGC 1333 over here. All the B objects are Barnard dark nebula. The LDNs are lens dark nebula. LBNs are lens bright nebula. The VDBs are Vandenberg reflection nebula. But this is a really beautiful area of the sky, and it's got lots of cool stuff in it, and takes a wide field of view to get it. Okay, now I got $5 here for anybody who can tell me what this object is without looking at your phone, what the reference designator is, and what the common name is for it. $5. Anybody? Who says you can't make money in astronomy? Anybody? Any takers? Nobody. That's because you guys don't read my targets list. That's LBN 420 called Galileo's Finger. It's a molecular cloud in Lacerda. It's a really cool object, I think, but very rarely photographed. I've only found like 2 or 3 other imagers who have ever photographed this thing. But it's really cool. Molecular cloud in Lacerda, Galileo's Finger. Cool, huh?
Why is it so rare?
I don't know why. I don't know why other people don't shoot it. I think it's a cool object. So, I mean, look, there's an infinite number of things. You know, when you go to Star Party and someone says, "Oh, I can't think of what to image." Oh my goodness, point your telescope anywhere, you know, because there's an infinite number of celestial objects to image out there. And yeah, I don't know why people don't image this one.
So what's the center of the finger, or what would you consider like? Is it the tip right there, the little orb looking thing?
Oh, Galileo's finger. I guess this thing is his finger. I don't know.
Okay.
I assume that's Galileo's finger. Dominic.
I think I know what Galileo's finger is. You know the thing that you just said that you think is Galileo's finger?
Yeah.
You see that part that kind of goes in like whoop?
Whoop. You mean this part?
Smoke.
No, like go down and then shoot. Like,
That?
just past it. You just
Here?
don't keep going up.
Left or right?
Keep going up.
Up. Up?
There. No.
Dominic, come on. What?
Down to the
We're a mix of you.
It makes a U?
There you go. Like that.
Okay.
It kind of looks like the tip of your finger, and like I think Galileo found it, and then that part kind of looks like that tip of a finger.
Okay.
And, like if you keep going up into it, kind of looks like a bent finger.
Okay, Dominic, that's great. You know, if Galileo found this object, that would be amazing. Since this telescope had like a 1-inch aperture. Okay. All right.
So
What?
I can see, it looks like one of those old wizard hats, right? And then his profile, and then his nose, and then that's his arm down, and that's his wand.
Okay. Okay, good enough. It's a molecular cloud in Lacerda. You guys passed up $5, I'm telling you. Okay, next imaging configuration. This is a 560 millimeter refract. What?
What was the field of view on that last setup?
Are you guys paying any attention to what I'm saying here?
They're going off at that.
5 degrees.
5 degrees.
5 degrees horizontal, 3.84 degrees vertical.
Gotcha.
Okay, got it. All right. Okay, the next one, 560 millimeter refractor force, 110
Yeah, I see that.
arc minutes. Yeah, okay, got it. Okay, F7, there we go. This is a picture of the Iris Nebula in Cepheus, NGC 7023. Some of these subs were from Fort McCavitt last year, some are from Okie-Tex this year. What I was trying to get with this, I don't know if you're going to be able to see it on this projector, but I'm trying to get all the dark nebulas around the iris. All around the Iris Nebula is a blue reflection nebula, but all around it, there's this dark nebula just everywhere. It's a really beautiful area. So look at it on my webpage. It looks a little better. Next one, Sharpless 2 132 Lion Nebula in Cepheus. This is a narrowband image. Some of these were taken at home, some taken at Okie-Tex, 12-minute exposures. So I've got one picture of it with stars and one starless with no stars. So there you go. There's with stars. There it is without stars. And this is one that actually looks like something. This is the Lion Nebula. So you look, here's the lion's head. There's his mouth. Here's his front leg. Here's his back leg. Here's his tail. See? Lion Nebula. All right. Last imaging configuration. Astrotech 1600 millimeter Ritchie-Cretan telescope, 38 arc seconds field of view. This was, that looks like, that's El Dorado Star Party.
Arc seconds?
Arc minutes. Thank you. Thank you. I misspoke. Arc minutes. Okay, this is Sculptor Galaxy. This is kind of an interesting object. It's actually not part of our local group that Brandon was talking about earlier. 11.4 million light years away. But for imagers, this thing is really bright. Okay, 12.9 surface brightness. The Andromeda Galaxy that we all think, oh, it's a bright galaxy, is 13.5. So this thing is actually brighter than the Andromeda Galaxy. So if you're ever out imaging and you want to see a bright galaxy, this is one of them. And I looked at this thing in binoculars too this year. You can put your binoculars up and see it too. Super bright. A lot of people don't image it because it's kind of close to the southern horizon, but it's a bright galaxy. Okay, last object. This is NGC 6822 Barnard's Galaxy in Sagittarius. This one is part of the local group. And, last time I looked at the local group, my memory was there was like 80 galaxies in the local group. And this time it says there are 134 galaxies in the local group. So I guess it's just, they're just finding new ones all the time. And then what I want to draw your attention to on this one, down here, this is another galaxy, but down here, we can actually see, this is a zoomed in thing, we can actually see these other objects in another galaxy. These are PGC objects. One of them, they're calling the Ring Nebula of the Barnard's Galaxy. Another one, they're calling the Bubble Nebula of Barnard's Galaxy. It's kind of cool to actually see celestial objects in another galaxy. There it is, and here it is close up. Cool. So you want to see these pictures, look at my webpage, holland-observatory.net, under recent, and you can see these pictures a little better. Any more questions before we move on?
Do you know distances for those really PGC? I mean, are those really, really far away?
They're small.
I mean, are they like?
Yeah. Well,
tens of millions or hundreds of millions of light years away?
Well, this guy is 1.6 million light years away.
Right.
And
in the local group.
Right, it's in the local group, and those are PGC objects within that galaxy.
Oh, those are in the galaxy.
Those are PGC objects within the Barnard's Galaxy. And also, I should have said, this guy is a Barred irregular galaxy. I mean, it looks kind of goofy. Usually we think of galaxies being spirals and all that stuff. This is a barred irregular galaxy. You buying it?
I wouldn't know to buy it or not buy it. I'm not even going to bid.
Was your question answered?
Yes, I thought those were other galaxies.
Oh, no. Those are it's interesting because I think the G in PGC actually stands for galaxies. Yeah. But the thing is, they're not the PGC catalog. When you look at it, it isn't just other galaxies. It's actually like this. It's actually can be other objects within other galaxies. Yeah, that is not a galaxy. That is that's like a ring nebula, like our ring nebula. And I saw one reference that said it was a planetary nebula. I saw another place that said it was not a planetary nebula, so I'm not sure what to think about that.
Probably just an H2 region with a big star cluster.
That's what I'm thinking. And then this one here, this is supposed to be a bubble nebula, kind of like our bubble, but I don't really see the bubble. Okay, any other questions before we move on? Yeah.
One of the other two really smudges in there.
I have no idea, Stan. I thought you'd know.
No.
Oh, okay. No, I don't know what they are. When I did my annotation thing, this was the only things that actually showed up as these two objects here.
In that previous slide, the other two were bigger and darker. See them on the bottom?
Yeah.
To the right of the PGC.
Yeah, and I can't explain that. All I know is when I did the annotation program, it only got these two, but I don't know why. You're right. There's other ones all over the place. But this is a really cool object. I mean, these goofy looking galaxies that are in our local group, they're kind of ugly, but there you go.
You're not going to find a pretty dwarf galaxy unless it's spherical elliptical.
Oh, this is a barred irregular galaxy.
Barred irregular galaxies are still with a dwarf.
Yeah, I know. I'm just giving you trouble. So, okay. Anybody else before we go on? Okay, we need to move on with the meeting here. Anybody else have anything to say? Okay, we're moving on in any case. All right, next up, we have Annie Wargetz. With Houston, we have Thousands of Planets. Annie Wargetz. She's come back. She used to be here from the University of Northern Southern North Dakota. Yes.
Sure. How am I supposed to follow your presentation? That was too awesome. I can't follow it. Yes. So we're going to be changing gears. I'm not talking about azimuth and declination and all of that because you guys are way better at that. I'm going to talk about something much closer to my heart, which is exoplanets. And a little bit about myself. I think what Doug is talking about is my master's degree, which was the University of North Dakota. Yeah. I was like, what? So I have my master's degree in space studies. I did human factors in heliophysics. And then I'm here tonight because I'm part of a program for NASA called the Solar System Ambassador Volunteer Program. So I'm very honored to be here and be back at JSCAS. I was here 10 years ago. Yeah, it's been a while. It's been a while. It's been a while. I apologize. This is going to be very bright. I didn't put any background because I knew it was going to be mashed together with everything. So it's just a white background with black text. I'm usually a lot more creative with this stuff. Okay. So brief personal history. Not to be cliche, but when I grew up, there were 9 planets in the solar system, and and that was it. 9 planets in the solar system. There wasn't even any mention of stuff outside of our solar system. We were taught the rocky planets were on the inside, the gas giants on the outside, and how all of that happened. And so I just, that's what you learned because that's what we knew. And I remember getting my mom, when I was very young, got me Astronomy magazine. I had hundreds of issues of that when I moved and donated them. But I remember in the late 1990s, started to see within some of the issues this topic of planets being outside of our solar system. And it was mind-blowing. And I just instantly remember thinking, well, all those textbooks have to get recycled or something because they're wrong. And then, of course, the discoveries started happening. And I actually happened to learn about the work out at Caltech, Jeff Marcy's team using radial velocity methodology and detecting planets one after another. And I still have it. I traveled to Toronto to see him speak at the Astronomical Society of the Pacific. This is from 1999. I was starstruck as a science nerd, and I went up after and just kind of stared at him. And my sister was like, "Don't you have any questions?" And my brain went blank. So one after another, they started discovering exoplanets, and it just became normal to hear more and more about them. By the way, exoplanet is the other term for a planet outside of our solar system. I got very happy when the Kepler mission happened. One, because Kepler and Brahe are my 2 favorite astronomy scientists, for lack of a better term. And then I was very sad when they had issues, and then very happy again when K2 happened, and then very sad when it retired. So it was kind of an emotional roller coaster, but I'm getting my fill with Gaia, JWST, TESS, all of those other missions that are happening. So I've been following exoplanets since the beginning, as it were. And so when Doug asked if I would talk tonight, I was like, ooh, exoplanets. Do you think the club would be interested in exoplanets? He's like, sure. And a very significant milestone happened back in September. I would have spoken about it sooner, but I wasn't here yet. I just moved back into the area. And I actually missed this announcement because I was getting ready to move. But back in September, there was a milestone of reaching 6,000 confirmed exoplanets in our galaxy. And I remember hearing about this when I found out about it and thinking, I remember when there was 0. And now there are 6,000 confirmed exoplanets. And on top of that, at least 8,000 candidates still waiting to be confirmed. So in theory, 14,000 exoplanets. And what blows my mind about all of this is that they're not all huddled in one section of the sky. It's not all one type. It's not all one type around one type of star. It's all of the different types of exoplanets at all different orbits, all around completely different stars. And our rate of confirmation is just accelerating as we get more and more ground-based telescopes and more space-based telescopes. Oh, by the way, backspace? Okay. If any of you want to take a look at this article, I have one of those QR code doodads in the bottom right-hand corner. If you want to take a picture of it with your phone, and that should take you directly to this article. I'll give you guys a second. I see some phones coming out. It had a tiny little dinosaur in the center, and I got rid of that.
I have a question.
Yes.
Do you know if any of these are compatible with life?
So there are a lot of them that would be considered in the habitable zone of their parent host star. A lot of them rocky. And what's great about the technology that's advancing now, especially with JWST, James Webb Space Telescope, if you guys were tuned in when they did the first release of data images from JWST, one of the images that came out was a spectrum from WASP 96b, and there was moisture in the atmosphere based on the chemical spectrum. So possibly, if you look at just, is it in the habitable zone of its star? Habitable zone meaning liquid water can exist, it won't freeze or boil off. And if you think about, oh, it has an atmosphere and it has a relatively stable orbit around the star, we can call it habitable. I'm doing air quotes because we can define habitable based off of what we find habitable, but who knows what's out there, right? So did everybody get the QR code that wanted it? Okay. So this was the milestone of 6,000 exoplanets being confirmed. Again, 30 years of searching, and the speed of confirmation, as I said, has just been increasing. So for context, 3 years ago, so just 10% of the 30 years ago, we were at 5,000, and now we're already up to 6,000. And the reason for that is just our technology advancing and becoming more readily available, more space-based telescopes to search, and more dedicated searches for it. You wouldn't have found many telescopes 30 years ago that were going to look for these because nobody thought they existed. But now that it's a known thing, more and more technology is being devoted just to that. Just like the Nancy Grace Roman Space Telescope that's going to launch next year. And about 100 of them have been directly imaged. And I don't mean the blue marble type imaged. It's a dot on a picture, but it's imaged. It's a confirmation of the planet being there. The other fantastic thing about this is kind of what I said, is that we're learning more about exoplanets. And what's crazy to me is they're finding planets the size of Jupiter that are within what, if they were in our solar system, it would be within the orbit of Mercury. They found Jupiter-sized planets that orbit their host star in 4 days. So a year is pretty short there. You have a lot of birthdays. Also, they're finding planets around double star systems, and they're actually finding planets that aren't around a star at all. Those are called rogue planets. So it's a confirmation of a planet that is not actually orbiting a host star, and dead stars, and also planets covered in lava. And I think I read somewhere, but please don't quote me on this, something about a diamond atmosphere. I think it's not actually raining diamonds. It's more about the chemistry of them, of what's showing up in the spectrum. So please don't quote me on that. You can't go there and get those diamonds, and and as it states, this is an effort of more than 30 years of dozens of space-based telescopes. We talked about Kepler and Gaia, and also just as much of dozens, if not more, ground-based telescopes, efforts by universities and research institutes. This is kind of, a dark slide. So this is what we consider as the exoplanet mission fleet. Some of them are retired, such as Spitzer. There's my beloved Kepler TESS, which is the Total Sky Survey, James Webb Space Telescope, the Nancy Roman Telescope, which is going to be looking at things like dark matter and dark energy and looking for exoplanets. Hubble has played a part in identifying some of these for them to later on be confirmed. Gaia, which I've mentioned, if you have not been to the Gaia website, please go there, because it's not as good as Doug's images, but they have a fantastic array of I'm just sorry. He's rolling his eyes at me. You can't see it. Please go to the Gaia website, because it's just amazing what they have found. TESS as well. I think you can tell I'm kind of biased towards these types of missions.
Could you give us a little explanation of how you observe a rogue planet?
It's going to be part of what I explain in 2 slides. Do you mind if I explain it in 2 slides? Okay. Thank you. That was a great segue. I'm all about if you give a person a fish they eat for a day, if you teach them how to fish, something happens, they can eat for life or something. So I feel like, a lot of us science communicators get up and show you fancy imagery and everything, but we never really tell you how to find it. And everything that I show in all of my presentations is easily, hopefully findable on the NASA website. So I've actually typed out the steps. If you don't want to bother with the steps, you can easily type science.nasa.gov/exoplanets. If you want it even easier than that, there's a QR code. And this is actually NASA's exoplanets page. And this is where you would go if you want to start tuning in and learning more about exoplanets and what's going on in exoplanets. Has everybody who wanted to click on that got it? Yep. Okay. Now, the really cool thing is the dashboard. I'm a data nerd. I love going and looking at what data is coming down from spacecraft and talking to DSN. I like the space weather forecast enthusiasts dashboard. I appreciate that they called us enthusiasts. And so this dashboard has just been fantastic. I'm going to show you some screenshots of it in just a second, but a couple of different ways to get there. You can type that really long URL. You can click on that QR or take a picture of the QR code. You can't click on that, sorry. Or if you go to the exoplanets page at the very bottom right-hand corner, hidden away is latest discovery data. And that is also how you get to the exoplanet dashboard, which is where I'm going to answer his question. Everybody who wants to follow along, followed along. Okay. All right. So one of the things that you'll see on there is the current composition of all the confirmed planets. And I talk about how they're characterized. So, terrestrial would obviously indicate that the surface is solid. It's not a gas planet, just like, Earth, Mars, you know them. A super Earth would be something terrestrial in nature that is larger than Earth, but smaller than Neptune. Then we have gas giant. We think of things like Jupiter and then Neptune-like. They have actually separated these out. They're usually combined when I've usually seen them, but I appreciate that they're separated out because then you can kind of take a look at them. But what's great about this is, again, it kind of hits home the point that I was making. There's 6, and also you can tell, I took this picture Wednesday when Doug told me I had to get my slides to him. There were 53 just confirmed just since September 17th when that announcement came out. But again, it's not all just terrestrial. It's not all just gas giants. It's a lot of them of each of the different types, which I think tells you something about the universe. The next part down on the website.
What's the difference between the Neptune-like and the gas giant?
Oh, I was just saying I'm not really certain what they've done to separate these two out because it's usually super Earth and Neptune-like. I don't typically see gas giant, so I'm not quite sure. It might just be a radius. It might be just bigger than Neptune-like. I'm not sure, to be honest. On this scale, we're talking about size. So I'm going to guess it's probably something quite larger than Neptune. So like the big super Jupiters, if you want to call them that. So the next spot down on the website is probably my favorite because I like going back and forth on the axis on the chart on the left. And so what this is it plots for you the mass of the planet. And then, of course, the color is how they found that planet. And then the bottom is how long it takes it to go around its host star, how long its year is. And you can see it's kind of squished in there between the 1 and 100. A lot of this is based off of the technology that we have access to at this time to find them. Really big stars really big planets close to their stars tug on their host stars a lot. So our technology can find those more easily. So this is where we're at now. And then over on the right-hand side, it breaks down the different methods. So this is how they find the planets, which would also be how they find the rogue planets. I'm thinking it's the micro-lensing, which I'll get to. And if you click on that down caret on the right-hand side, when you go to this website, it explains what these different methods are. So transit is, if you're shining a flashlight and then you pass your hand in front of it, whenever your hand is in front of the flashlight, obviously, the flashlight would appear to dim to an observer. And that's what we're measuring here. It's cyclical decreases in how bright a star is. If it's cyclical, that means something's regularly passing in front of it. So that's called the transit method. Radial velocity is the one that I told you about, kind of where you have, whenever you have a planet orbiting its host star, it's actually tugging on that star a little bit. So it kind of wobbles in its place. And so the radial velocity is measuring that wobble. In other words, and that's how they can say, oh, there's an object there. The microlensing is that the light coming from the planet or around the planet, the exoplanet, is bent, the star, I'm saying the wrong word, is bent by something there. So the host star light is getting bent by something going around it, and it's shifting where that light is. So are you familiar with the concept of microlensing? Okay. I'm not, no disrespect. I just wanted to know in case I can keep going. Well, I meant in general. In general, these are all the different ways that they find the rogue planets. These are all of the different types. And to be honest, I think one of the 100 that we've directly imaged is one of the rogue planets. If I'm not, I might be wrong. But you can certainly go on this website and they have the information about the rogue planets. So I think it'd be better maybe, because I don't know, I don't want to make something up. But I want to say one of the 100, maybe a couple of the rogue planets are direct imaging. I haven't been turning my pages. Okay. Let's see. Okay, I do really think it's fun to go and play around with this chart on the left, because as I mentioned, one of the things for me is just thinking back to when I was told in a classroom, 9 planets, that's it. And now this chart with 6,053 planets that we know exist outside of our solar system. So you can actually drag the cursor along the bottom axis and you can go backwards and forwards in time. And so this is where we started in 1999. So yeah, I heard you guys got, yeah, exactly my reaction. So we went from something like this to this, and it's just incredible how far we've come. So if you want to scan that QR code, or if you go to science.nasa.gov/exoplanets, you can click on latest discovery data in the bottom right-hand corner. Try to give multiple ways of getting there. Did you get it?
Just that sometimes NASA's websites change and they don't always have. Okay.
Yeah, they did just redo a lot of the websites, and it broke a lot of my links. So I'm very careful to go back and double check. Okay, I think. Oh, whoops. That's it. I don't, yeah. Oh, okay. Are there any other questions? Yes?
So does somebody name all these planets?
Actually, so like I said in the beginning, the planet spectrum that we received from James Webb was WASP 36b. Have any of you guys heard of TRAPPIST-1, which is my absolute favorite? So TRAPPIST is actually the observatory that found this solar system of 7 planets. And it's TRAPPIST-1 because it was the first one that observatory detected. And then each of the planets are named the letters of the alphabet starting with B. So yes and yes. That it's not like Jerry or Bob or Lindsay. It is like WASP 76b, TRAPPIST-1c, those kinds of things. And it's a specific nomenclature for observatory that found it, and then so on and so forth. So they have names. I think you can call them Bob, Lindsay, whatever you want. Planet Bob, and we need to get a Planet Bob.
Was TRAPPIST-1 also called TRAPPIST-star?
I don't know that. But Doug? I've asked my resident expert, and we're not sure.
Think SpongeBob together.
Sweet victory. Any other questions I can try to answer? No? Okay. All right, now I'm going to go sit down. Thank you. Oh, hey. Shameless plug for January 9th. the meeting, I'll be talking about Parker Solar Probe. So
She's our main presenter next month.
thank you for
We
that.
got a preview. Next up, Reed, C-Star S30 Smart Telescope explores the universe with precision and portability.
Thank you. This is Members Minute, and I'll try and stretch it out to a minute. My son was kind enough to make the presentation for me. And as you guys are painfully aware, I'm not quite good with computers, but yeah. I got a C-Star S30 for my son-in-law. He let me take it with me to Okie-Tex. I still haven't returned it. But I've got it with me today if anybody wants to see one. Again, just a small telescope. Yeah, battery, everything works on it. You just set it down on the ground and it goes off taking pictures. Now, my pictures aren't anything like Doug's. But in saying that, I get this quality of picture in about 20 or 30 minutes where, Doug takes hours and weeks and months of exposures. But again, I get these and I can send them out on my cell phone. Friends and family seem to like them. But they haven't seen Doug's. But yeah, this is what you get. Again, it does solar. It does quite a bit, as you can see. It's a nice little telescope, toy. It's kind of fun. They're on sale now, $349, whereas everyone else's telescope is thousands of dollars. But $349, get it now. I saw it today, still on sale for $349. And yeah, it's very easy. It does all the searching for you. It just tells you what's best in the sky. And you just push the button and off it goes. Yes.
So does it uploads the pictures to your phone?
Phone or tablet. Yeah, just right away. It takes pictures at 10, 20, or 30-second images and then automatically stacks those as it goes along.
Can you go back one?
I don't know. That's it, this one?
Yeah.
But yeah, it's a lot of fun. And like I said, very easy. Does anybody have any questions about this?
It has both a sun filter and a moon filter on it. You can take a picture of the moon as well.
Yeah, you can take pictures of the moon. You can adjust the brightness, the contrast, everything, yeah. And yeah, it's got a little solar filter you put over the lens.
Okay, so that's separate. It's not built into it yet.
No.
Actually, there's parts that get attached.
Yeah, you got to attach it. But any other questions?
Yeah, yeah, you have the one filter, but I mean, can you buy them in a pack with, different filters that you're trying to use?
Now, they say you can get an adapter and put filters over the lens, over the front lens, but I haven't done that yet.
No?
But I've seen on the internet it can be done. But, all right, well, if anybody wants to see one, I've got a C-Star over here. Yes?
Did it come with the filter and everything for solar imaging, or was that an additional purchase?
No, it came with it. Yeah.
You get commission. No, I'm joking.
All right, anybody else? All right, thank you much.
Okay, Rick with light frames, dark frames, flat frames, bias frames, and their role in creating an astrophotography photograph. Come on, Rick.
Okay, and I asked, it's 9:30.
Come on.
Do I want to get in between that and my pizza. Do we want to do this in January?
It's up to you. You guys want to get out of here? Or you want to hear Rick's presentation?
Yeah.
You want to do it next
I wanna
month?
get in between my pizza.
Okay.
Yeah, I'll just do it in January.
Thank you, Rick.
And
Okay.
as long as I don't have to go follow you.
I'm not going to do a presentation because mine was supposed to be 5 minutes. Why not be in it forever? Okay, we're going to zip past. We're going to do door prize. Can somebody get me the door prize bucket, please? Help me out here
Did everyone get a ticket?
quickly. Okay, so next month. Oh my goodness. Come on, guys. Move. Okay, next month we're going to have Annie on January 9th to boldly go closer to the sun than ever before. Annie, you just saw her. She's great. She's going to be here next month. And now we're going to do door prizes. As soon as I get the door prize bucket. So look at your tickets, see what your number is. Justin, give me the bucket. Come on. All right, get your number out. 214. 214, going. Any with 214? Gotta look at your, oh, is it you? Oh, get down here, Dominic. All right, Dominic. Hold on, man.
Last time I was up here, I was much more smaller.
I know, I almost didn't recognize you. Okay, I got a moon map. I got a decal you put on your card that says, "Let's sleep under the stars." Is that cool? Oh, wait a minute. I have a little blue thing that makes a bunch of crazy lights. I can get it to work. You want that? It doesn't work.
Let me try.
Okay, you try it. I have a second one here someplace. There it is. You want that? Dominic, make a decision.
Yes.